Okay, all right. So welcome everyone. Yesterday was fun. Today I'm hoping to be fantastic. We already know our speaker, Edward Pai, a good one of Ghana's finest programmers. Oh, well, let's see, maybe after next year, you'll be after me when I also power up in machine learning. Pai, so get ready, I'm coming for you. All right, so I hope you guys enjoy. Please try and make notes, okay? Try and make notes, ask questions. That's what makes teaching fun. That's what makes teaching fun. And Oxygen, please stop hiding, okay? Stop hiding. All right, Pai, let us rock and roll.
You can see my screen, right?
Yes, sir.
Okay, all right, great. So we go to Colabs. The approach today is going to be the reverse of yesterday. I start with practicals, then I will go to the board to explain things to you so that you can map what you saw to the explanations I'm giving you. So we go to colab.research.google.com, and I have some notes on my right-hand side to guide me through what I want us to focus on. So, like I said, today we are going to learn simple linear regression. And by the way, you can name your notebook. So to do that, you just click in here. So you see it's untitled. Untitled 39 means I have 39 untitled ones, but I can just say simple linear regression. Then I will say hello AI to distinguish it from other ones that I have. All right, so what is linear regression? We use linear regression when we want to learn the relationship between two numbers, okay? For example, we know that there is a relationship between your height and your weight. Unless you are extremely anemic, you cannot have a height of 1.8 meters and weigh something like fresh bread.
I think Ola will do.
Who?
Ola.
Okay, no, Ola. So you see, Ola is not that tall, but he will have a very great weight. So there is a relationship between your height and your weight. Now, the question is there a way we can learn a pattern in this such that when we get somebody's height, we can automatically estimate the person's weight? The key word here is estimation. Estimation because your interpretation of what the model gives you depends on the sensitivity of the application. Okay? For example, it doesn't hurt if I estimate your weight wrongly by an error of plus or minus 5. Okay? Maybe I'm giving some medication and it depends on your weight. If it is very critical that I need to get your exact weight, then you can't rely on a regression model because inherently it is an estimation, but it's a better estimation than guessing. Let me give you an example of where you can apply regression in electronics. So I have in my hands here 2 different electric motors. This one is from a company in Japan called Robotis. So as you can see from the name, they make highly accurate motors for serious robotic projects. And this is how their motors look like. This motor here has its own microcontroller in there. It has a temperature sensor And the protocol for communication is very different from these Agbalagba motors that we have been using. Now, what is the difference between these two motors? This one is highly accurate. How does it achieve the accuracy? Because it has a microcontroller, there is a software on it that makes software corrections to the errors from manufacturing. What do I mean by errors from manufacturing? If I take two of these motors and I apply the same voltage to the terminals, there is no guarantee that because they are the same motors, if I apply 3 volts to all of them, the RPM is going to be the same. There is no guarantee because of manufacturing problems. The magnetic flux, the magnetic strength of the magnet in there, you cannot achieve the same. Even if you manufacture them in batches, you cannot. The number of windings of the coil in the motor, you cannot achieve the same. The weight of the shaft, you cannot achieve the same. And all these factors affect the RPM. So this one has a computer in itself. So if you are using it to build a robot, you send instructions from your computer to the computer on this motor, and that computer will make sure that it achieves the RPM you want using a technique known as PID, proportional integral differentiator, whatever controller. But these guys, it's like you need to be a living legend to get serious accuracy with this. To be able to control the RPMs, you need an encoder, either a magnetic encoder or a light encoder, optical encoder, to count the RPMs. And you need a control algorithm to be able to achieve that. Now, I'm telling you this because I'm talking about regression. And I said, where you apply it depends on the sensitivity and the importance of the solution you are building. If you ask me to build a robot that is going to perform surgery on human eye, I am safe when I use this guy because I can manipulate the 10 angles to let the end effector, let's say the hand of the robot, reach a particular point in 3D space because I can accurately control the angles that I move this. I can't do with this one. So if you attempt to build such a robot with this motor, you will aim for somebody's teeth, and by the time you realize you've took somebody's eyeball, which is highly unacceptable. But in everyday normal robotics, you are building your toy car, you are building your self-driving car, you are trying computer vision on a robot, and you want to do what is known as pose estimation or orientation or position. You see, most of us, the level we are now, when we say we've made a robot, typically from Ghana, when we say we've made a robot, typically from Africa, by the way, when we say we've made a robot, it means we've put motor under something and there are wheels, and we just turn it on, then it go. But when you make a real robot, you need to be able to tell where in space the robot is. Okay? To be able to do that, that is when the senseless questions and the senseless statement people make begin to become annoying. Like, what do I do with pi r squared? You measure the circumference of your wheel, you multiply that with your RPM, and then at any time, you will know where your robot is in space, in 2D space, because it drives on the floor, X and Y. Now, here is your challenge. You are not able to guarantee that because these motors are coming from the same manufacturer, applying the same quantity of voltage across them is going to achieve the same RPM. But like I said, a better estimate is much preferable than a simple guess. So what you can do with regression here is you will apply, let's say, 1 volt to this, and then you use a tactometer. I have one line around. It's a device for counting RPMs. Then you count the RPM you are achieving at that voltage, okay? So over here, what are we trying to do? We are trying to use voltage to predict what? RPMs. Then you increase the voltage to 1.5, you measure the RPM. Voltage to 2, measure the RPM. 2.5, measure the RPM. as much as you can. Of course, you can't cover all the voltage range that this motor can take, but you cover enough. Then you will use linear regression to learn the mathematical relationship between the voltage applied and the RPM. So if I'm going to use 4 motors on my robot, and I want to avoid the use of encoders and buying this motor costs $50 one. Some of them cost $1,000 for one motor. If you can't afford that, you have to go for this Alaba Market motor. Now, for all 4 of the motors, you need to use regression to estimate the relationship between the voltage applied and the RPMs that you'll be achieving. I share this because I know that amongst us are people who are interested in electronics. There are people who are interested in business. There are people who are interested in finances, other things. That is why I will make my examples span all these domains so that you know when to apply. So let's go to the medical field. There is a mathematical relationship between your height and your weight. It is not all the time that we will have both devices around to measure. And in certain situations, it is okay for us to estimate. So if I know your height, it is okay for me to estimate your weight and administer some not so serious medication to you. So over here, over the period, the hospital will have information about the height and weight of people. Then we can use regression to learn the relationship between the height and weight. And now when we see a new person, we just input your height, and our model will, at a certain level of satisfactory accuracy, tell us your weight, and that is completely okay. So that is what we are going to learn. So in summary, regression helps us to mathematically establish a relationship between 2 numbers or 2 observations. What we are going to work on today, we are going to assume that we have made 2 sensors and we have put them to measure some physical quantity. At the end of everything, I will tell you which physical quantity my data represented. But so there are 2 sensors, they are all measuring the same quantity, okay? Let's say 2 sensors, all measuring light, but they are measuring light in different units, okay? The same way I can measure length in either centimeters or meters or millimeters or inches. Let's say we have 2 sensors. One can measure the light intensity in whatever is the unit for measuring light intensity, and another is measuring in what, Eric, what's the unit for light intensity?
You can do it in lumens or candle or whatever.
Yeah. So one is measuring in lumens and one is measuring in candidiasis, so whatever he said. You you get a point. Then now we want to find a way to learn the relationship between them. So like unit conversion without actually writing code to do that, okay? I'm going to use some things I haven't taught you. So 5 minutes, I'm going to show you those things, and then we will start working on the regression problem. Yesterday, I introduced you to Numpy, which is for vectorized computation. So I import Numpy as NP because we're going to use this guy a lot. And then let's wait for Google to finish whatever they are doing and then give us. Yeah, okay, now it's done. Now, I'm going to teach you some Numpy functions, okay? If I generate data, say data is equal to np.arange. This arange then helps you to generate numbers between a range. So if I say -10 to 10, basically I'm generating all the numbers between -10 to 10. So what do I get? I get -10, -9, -8, blah, 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 0, 1, 2, 3, 9. So the right endpoint is not included, it's excluding the right endpoint. So if you just want to generate something, anything, okay? Yesterday I taught you how to check the shape. So this is going to have a shape of 20. 20 by what? At this point, the matrix is confused, the vector is confused. Is this a row vector? is it a column vector? A row vector is a vector that is written and all the numbers are on one row. A column vector, all of them are on one column. And a multi-dimensional, you have multiple rows and multiple columns. Okay, great. So NumPy offers the ability for us to reshape our data. The method is called reshape. So if I say data is equal to data.reshape, if I want all of these to be a column vector, the first argument to reshape is the number of rows that you want. Okay, so look at this. It has 20. It has 20 items. 20, so I can make it 4 by 5. Now, when I print data, what do you see? You can see that, you see, in NumPy, your matrix is a list of lists. Each list within the list is a row. So you can see that we have 4 rows and then 5 columns, because I said data is equal to data.reshape. So I'm saying the 4 is the number of rows, the 5 is the number of columns. I can also reshape it this way. I can say data is equal to data.reshape -1, 1. If I specify -1 for an axis here, I mean row or column. If I say -1 for the row, it means I don't care about it. I just care about, I want 1 column. So whatever you have to do to make sure that I have 1 column, because now our data, in fact, let's check the shape of data before we reshape it again. So you see that now data is 4 by 5. It's a 4 by 5 matrix, right? Now I can say data is equal to data.reshape -1, 1. Now I say data.shape and see something. Now data is 20 by 1. So it has 20 rows, 1 column. Okay. These things are going to disturb you a lot, the shape of your matrices and vectors. So this time is not enough for me to show you everything. That is why I have pre-recorded videos that you can watch to learn the details. But I'm only showing you this because we will need it in what I'm going to show you very soon. Okay. Now we have data. We can save it into a file, because most of the data that you'll be working with will come from files. So in as much as NumPy makes it possible for you to generate data, it also makes it possible for you to either read from a file or write to a file. So I'm going to show you how we can save our data to a file. We can do, I made some simple steps here to guide me to know which ones to show you and which ones not to show you, not to waste your time. Okay. All right. So I can say something like data.save TST. I think it's save TST. And then all that you have to do is to provide a path. So I'm going to call it data.tst. And then you pass in the NumPy array. I'm sorry, it's supposed to be np.savetst, because the savetst function comes from NumPy. When you do this on Jupyter, you ask yourself, where in heaven's name has the file been created? You come to the left-hand side here, you see that there's this folder here. That is your file system. When you click on it, you can refresh to see, but this is the file that we created, the data.tst. It is right here. So you can download it onto your local computer. You click these donuts, whatever, those 3 buttons, and it gets downloaded onto your computer. So you can open this file as any regular test file. So over here, I have it here. When I open, it's just a test file containing the numbers that I generated. Don't bother so much about how it has been represented in the test file. When you read it back, NumPy knows how to get the numbers that you put back. Okay. I'm doing this because the data set we'll be working with, I have created it already. And
hello, Pi.
Yep.
Mohammed, I cannot mute you. I don't know why, but can you please mute your mic?
Yeah, please, if you're not talking, kindly mute yourself so that
thank you.
We don't hear your private conversations. It's not nice if a lady breaks up with you and it shows up in our conference. Okay.
All right, let's continue.
So I've shown you how to save data to a file. You can load this data back, okay? So I can say loaded data is equal to np.load tst. And over here, you just have to provide the path. So data.tst. This is going to load back what we wrote into the file. So it's going to load whatever is in here. So now if I print loaded data, I get the data we generated back in the shape that it was when we wrote it to the file. There are multiple ways that we can write. We can write as CSV, we can write as a zip file and all those things. That is not all important. I have the videos that goes into details, but I'm just showing you these because I'm going to use them to explain linear regression. Okay, so now we know how to save data. We know how to load data. Now let's get on to linear regression. And like I said, there are levels of understanding when it comes to building AI models. The first level is you are using libraries, but you don't understand what is going on under the hood. And that is the approach I'm using. I'm going to show you how to use these libraries, but by Friday, I would have shown you how the actual learning works, where we talk about calculus, gradient descent, and how the mathematics involved in the learning process. But for today, I'm showing you how to build it so that you can appreciate what you can do with these things. All right, so for that, we are going to use a library called scikit-learn. So sklearn, scikit-learn. Let me actually open it here for you to see. So you just say sklearn and linear regression. sklearn is a Python library that helps you to write classical machine learning models. So they have already implemented all these algorithms with a very consistent API. So if you want a linear regressor, just create an instance of a linear regression model. And then we call fitting. Fitting is you are giving it those two numbers, and the linear regression model should find the relationship between them. Like I said, we are doing a top-down approach. So we are creating a linear regression model, then we see the magic. Then now we'll go back to the board and I will explain to you what is involved in the learning. So when you come to scikit-learn, they show you an example of how to use everything that they have in their library. So if it is linear regression, you import it, you create an instance, and then you fit it. Okay, so I'm going to import it. And by the way, these Colabs notebooks have all the data science libraries that you need. You don't need to install. There's a way to install a third-party library if you need it. And when we get there, I'm going to show you how to do that. Okay. So I'm going to import. So we say from sklearn.linear model, import linear regression. Yep. So this imports linear regression from the sklearn library for you. Then all that you have to do is to create an instance of the linear regression class, and you give it your X and your Y. Now, what is the X and the Y? I told you that in the motor example, we were learning the relationship between voltage and what? RPM. So the voltage becomes your X. Voltage is the predictor. Voltage predicts, voltage determines the RPM. You see, you want to answer this question. What is your X and what is your Y? Depends on how you frame your question. With this motto, we are interested in the question, if I apply X amount of voltage, what is the RPM that I'll get? So your X becomes the voltage. Voltage is the thing that you know how to readily generate. I mean, I can just put my bench power supply, set it to any voltage, and I get a voltage. I don't need to do magic to get voltage. But the RPM is what I'm interested in learning. And I want to learn the relationship between voltage and RPM. So this is going to help you to kickstart your project, even when you don't have your magnetic encoders around. And I know your problems. For those of you in Africa, when you order from AliExpress 1 month, by the time the sensor comes, the determination to do the project has left you. So these techniques will help you to get something going whilst you wait for DHL to hopefully deliver your sensor to you, okay? So the X is the voltage, and the Y is called the dependent variable. The X is called the predictor. You see, it determines something. and the y is the dependent variable. You can also call the x the independent variable. The predictor is independent on nothing. Voltage, we are just interested in what RPM I get from which voltage. So then the dependent variable is the output that you want. In machine learning, our outputs are usually labeled as Y, and our input data is usually labeled as X. So you know what it is. All right. So we have our linear regression models here. I'm going to upload files here because I have already generated some data set that we are going to use. The way to upload files, I think you click on this, upload to session storage. So when you click on this, you browse to wherever you've kept it. I have data sets on my computer and I have x.tst and y.tst. I click open. Yeah. So it's telling you that, you know, Google is giving you this computing resource for free. They are not giving you a place to store your files forever. So your notebook is alive for a certain number of hours. If that hours expires, the storage is ephemeral. Whatever you put in there is going to be cleaned. So it's not a place for you to store permanent data. So the best way, if you are working on a model that you have to train for days, is you keep your data on another server where it is permanent, then you reference it from here. Because once the machine restarts, the storage they give you is ephemeral. It is cleaned and you don't have access to it. That was the warning that it was giving me. All right. In this X, I have some data. In this Y, I have some data. I'm not going to tell you what it is, but when we finish, you see the magic of machine learning, how this linear regression model will learn to automatically convert from one thing to another, and we didn't have to code it, okay? So I'm going to load my X. So I'll say X is equal to np.loadtst because it's a test file, and it is in this folder, x.tst, okay? Then I'm going to load my Y is equal to np.loadtst, and it's also in y.tst. So I've loaded the two of them. Let's see something about them. If you print X, it's just a bunch of numbers from -100 to 100. And then let's see Y. Quick, what happened? Yep, it's also a bunch of numbers. But trust me, there's a relationship between this and this. There's a relationship between this and this. So pairwise, like, let's see the shape for both of them. If I say x.shape, in fact, let me print them on one line. So I'm going to print x.shape, y.shape. You can see that they all have the same shape, right? 200, 200. They are vector of 200 items. So it's two different vectors. Each one of them have 200 rows. And the corresponding items have some mathematical relationship. I know it, but the model doesn't know. It's the job of the model to learn it automatically. So we are going to use this. Now, we need to create an instance of this linear regression thing, and then we fit our data to it, okay? But in scikit-learn, it expects your data to be in 2 dimensions. This is in 1 dimension. So what do? We reshape it like I showed you. I want it to be 200 rows by 1 column. This one is just 200 by what? You are confusing it. So I say x is equal to x.reshape. I don't care about the rows. I can actually specify 200 by 1, but if I say negative, it will know that it is 200. It will count it and then it will do it for you. Then I'll say y is equal to y dot, 10 minutes, don't worry. Y dot, I'll try to finish within this 10 minutes. Y dot reshape -1 and 1. So now if I print x dot shape, y dot shape, y dot shape again, now they are 200 by 1, 200 by 1, okay? So now let's create our regression model. I'm going to call it model here. Is equal to, I'm going to create an instance of a linear regression. So I have an instance already, then I can call the dot fit. Fit is where the learning is happening. I will explain to you why it is fit when we go to the board and then we are doing some calculations. But I want you to learn the relationship between X and Y. Okay, let's run this cell. It has finished because this data is not much. It's just 200 by 200. That's nothing for even the CPU to do. We didn't even have to use GPUs here. Okay, now the model has learned something. How do I know what the model has learned? Okay. Well, because it's linear regression, the learning of linear regression happens through learning a y-intercept and a slope. Don't worry, when we go to the board, you understand it. So I can see what the model has learned by saying model dot coefficient is 1.8. Don't worry, I will explain to you why it's 1.8. And model dot intercept. Now, let me disclose to you what data I gave to it. The data I gave to this model is temperatures in Celsius. The X are temperature values in degrees Celsius, and the Y are the corresponding values in degree Fahrenheit. Let's see what is the conversion between Celsius to Fahrenheit. To convert from Celsius to Fahrenheit, you multiply the Celsius value by 9/8, 9/5. What is 9/5? That is 1.8. You see? 1.8 right here. So you multiply the Celsius value by 1.8 and you add 32 to it to get the value in degree Fahrenheit. Okay? So now, all of a sudden, we have built a model that can convert, any temperature value from degree Celsius to degree Fahrenheit. The question is, how did it know that the relationship between Celsius to Fahrenheit is multiply the Celsius by 1.8 and add 32 to it? Because the truth is, if I come here to Google and I try to convert, let's say 150 degrees Celsius is what? 302 degrees Fahrenheit. Let's see what our model tells us. To use the trained model, you say model.predict, okay? And to predict, you pass it a NumPy array of the values that you want it to predict on. So I'll say np.array. So I'm passing it a NumPy array, and it should be two-dimensional also. So what did I convert here? 150, right? So let's come here. I ask it to predict on 150. What does it give me? 302. What is amazing about this is, you see, in my data set, the data set runs from -100 to 99. It never saw 150. That is what AI models do. They learn the pattern and they generalize it because this thing is mathematical. It is purely mathematical. So once it learns the mathematical relationship, even if it hasn't seen the data before, it can. So you see, yesterday I told you that in machine learning, you are letting the computer learn something without you explicitly telling it what it is. But through the power of mathematics, the computer has figured out that between these numbers and these numbers, there is a mathematical relationship between them. And that relationship is that you multiply it by 1.8 and you add 32 to it. So to convert from degree Celsius to degree Fahrenheit, this model has learned, and now it can convert any temperature from degree Celsius to degree Fahrenheit. Any question? We have 5 minutes. Let's take questions before, when we come in the next section, I'm going to do the theory, explain to you how the learning actually happened. If you are seeing stars, if you are seeing, it's like, you feel like giving up, just unmute yourself and let's find you. If you are lost in the bush, let's find you before a lion chews you. Because on this journey, when a lion chews you, you need a team of buffaloes to catch you. Eric, I think you are muted.
Yeah. I think with this, something similar in mathematics, I think in SHS or something, where you are given a table and you plot the graph to find the really, that's what is actually happening here.
Yeah,
that's interesting.
So the model is actually doing this thing for you.
Yeah,
but you had to plot a graph. See, let me show you something. We can plot. I can say import matplotlib.pyplot as PLT. And please go to my YouTube. I have tutorials on Matplotlib also. Learn why I'm importing Matplotlib, but it just helps me to plot things. Okay, I'm going to plot the X and the Y. So if I say PLT dot plot X and Y, I'm basically just plotting the degree Fahrenheit on the degree Celsius on the X-axis and the degree Fahrenheit on the Y-axis, okay? Now, this data is fictitious because there's an absolute mathematical relationship, so none of the points are moving away. That's why it's a straight line. Even if I do a scatter plot, you still see a straight line. But what the model did is, it had to draw a line between all these points. If it is able to draw a line between all these points, then it gets the mathematical relationship. Why? The line depends on two things. The gradient, if I change the gradient of this line, the line will change, okay? If I make the gradient higher, to go this way. If I make it lower, to come this way. And the intercept on the y-axis. If I extend this line and if I change the scale of my plot, this line will cross the y-axis at 32. I'm going to explain to you the mathematics after the 2 minutes is up, and then we join after 1 minute. So for now, let's use it to ask our questions.
Yeah, and
hello, Pa.
Yes.
I think.
Okay.
Yeah, I think this is following that famous Y is equal to mx plus c.
Exactly. So now
Okay.
it is the job of the model to find m and c.
And then c.
Yes,
Okay.
because you have given it x, you have given it y.
Y.
The job is to find m and c through some mathematical means.
so can I say that behind the scene, it's doing some brute force stuff, right? Because trying to get...
Unfortunately, it is not brute force. There is a very deterministic calculus for doing that. It is called gradient descent.
Gradient, okay.
Yeah.
Yes. Because you see, this is a rather very simple solution, a rather simple model I'm using to introduce you to it. But if we are building something like facial recognition, there are giant of like millions of parameters. Brute force will not work because you see, when you touch one, all the others will be affected.
Yeah.
So brute force is not going to work. So there needs to be a deterministic mathematical approach to doing that. And that is what gradient descent does for us.
All right. And when do you use Panda and when do you use...
okay, so scikit-learn is for building models. Pandas is for working on spreadsheets or tabular data.
Oh, okay.
Okay, and then Matplotlib is for plotting. But they all work together. Matplotlib, Pandas, all depends on Numpy. They use the Numpy data structures. So
Hi.
if okay, yeah, question.
Yeah, with a small background in astronomy, especially radio astronomy, we're able to get large data from space. And we do reverse engineering to see if we can generate images from the waves that we are getting from space. And most of them are done with Python. And a lot of progress hasn't been done in terms of AI. Is there a way that we can train like a system that will automatically get the information? As soon as it gets the information, we'll be able to go through all the process and then retrace the images?
The possibility depends on if you have enough data that captures the requisite pattern in them. So you have had giant data. Do you also have the giant number of images that have been generated? If so, then you just use the giant data to be your X, the images generated to be your Y. Then the new giant data that comes in should